So I'm the first presentation. My name's Jeff Speck, by the way. I didn't even introduce myself. I'm the moderator of this session, but I'm also the first presenter. So introduce myself. My presentation is an introduction to some of the things that you're going to be seeing in much more detail from the other presenters. Let me look at a few questions here. Everybody knows what structural lightweight concrete is? Everybody know what internal curing is? If not, you'll find out by the end of the day. About 4 years ago, I was on a Zoom call, a webinar, where the presenter was telling people don't use lightweight concrete because it's not sustainable. And I was floored. I said, how can he make a statement like that? Well, he was only looking at one aspect of lightweight concrete. He was looking at the production processes for expanded shale, clay, and slate lightweight aggregate, which is similar in many ways to the production of cement. And we all know how evil cement is. So from a green perspective, that was what he was looking at. So we're going to delve into more detail than what he was doing, and hopefully by the end of the day, you will come to a different conclusion than the one he wanted everybody to come to. Have you ever been involved in a project that used lightweight or specified lightweight concrete, and there was some hesitance on the part of either a designer or a contractor or an owner to use lightweight concrete for one reason or another? I'm going to give you a lot of reasons why we should overcome those objections with all the benefits of using lightweight concrete. Is lightweight concrete more expensive than normal weight concrete? We'll answer that question, hopefully. And is it a sustainable option? We will come to the firm conclusion that it is the sustainable option. I'm like a good lawyer. I never ask a question that I don't know the answer to already. And the answer to this is yes. It is a sustainable option. So what is structural lightweight concrete? In case anybody doesn't know, ACI defines it as lightweight with a lower density, made with a combination, either made with lightweight aggregate or a combination of lightweight and normal weight aggregates, having an equilibrium density generally in the range of about 90 pounds per cubic foot up to 135 pounds per cubic foot, which is a recent change. The definition used to stop at 120 or 125, depending on what you're looking at, and then you had a gap between 120 or 125 and 135 where normal weight concrete starts. So what do you do in between? So the definition was changed to take lightweight all the way up to 135, so you can design it according to ACI 318 and use the design adjustments there. Lightweight concrete's been around for centuries. Actually, some lightweight concrete predates this Pantheon project the Romans built. But this is probably the first project in which lightweight concrete was intentionally used and the lower density was taken advantage of. And they used volcanic rock that was available locally. The Roman engineers adjusted the density of the concrete as they got higher in the dome. The dome of the Pantheon is what has the lightweight concrete in it, and the density of the concrete is the lowest at the top of the dome. So the other lightweight concrete before this might have been lightweight just because that was the locally available aggregate. But these guys knew what they were doing and did it intentionally. Modern lightweight concrete traces its roots back to the early 1900s and a gentleman by the name of Stephen Hayde, who was a builder and a brick maker. And he was making brick in the Midwest out of shale, and he was using beehive kilns, which have variable temperatures, and he noticed that inside the beehive kilns, some of the brick were bloating instead of staying a uniform size. And so he said, well, maybe I could intentionally make this material bloat and do something positive with it and create a lightweight aggregate. And so he patented the process of using a rotary kiln, which was a more consistent way to make the material bloat than the old beehive kilns and other processes. So he patented the process, rotary kiln process to produce expanded shale, clay, and slate. And during World War I, he gave the federal government of the United States the rights to his patent so that they could use it to develop lightweight concrete specifically for shipbuilding. And during World War I, concrete ships were built. The first one that was commissioned was the USS Selma that you see here. And during that process of developing lightweight concrete for shipbuilding, things happened like the development of the slump test. That's attributed directly to the development of lightweight concrete back during World War I. So, as most federal government projects happen, it was a little bit late coming to fruition. The ship was commissioned and launched right after World War I ended. So, I don't know about being $1 short, but it was a day late. But the process repeated itself in World War II. Shortage of steel. They started building concrete ships again, lightweight concrete ships. And over 100 concrete ships were built in total between World War I and World War II. Some of those World War II era ships are still floating in the water at the mouth of the Powell River today. And a testimony to the durability and strength and viability and watertightness of lightweight concrete. A little counterintuitive that it's watertight. All right, why do we use lightweight concrete? Well, the first big reason is density reduction. What's the benefit of density reduction? Well, we'll get into that, but typically the amount of density reduction is about in the 25 to 30% range compared to normal weight concrete. And a benefit of that density reduction is an improvement in the fire resistance of the concrete. By and large, the fire resistance of concrete is based on how long it takes heat to pass through the concrete. Lower density concrete transmits heat at a slower rate. So a slab of a given thickness achieves a higher fire rating if it's lower density than if it's higher density. Another way of looking at that is it takes only about 3 1/4 inches of lightweight concrete to achieve a 2-hour fire rating in a fire test, as opposed to about 4 1/2 inches of normal weight concrete. So you have potential for a slab thickness reduction of about 28%. Combine the lower density and the reduced thickness of the floor slab, and you get a significant reduction in dead load from the floor system. Normal weight concrete floor system on steel deck is about 65 to 70 pounds per square foot. Equivalent lightweight slab is about 35 to 40 pounds per square foot. Pretty big reduction, about 35-45% reduction in the dead load just from the floor system. You also have the potential for reduced transportation costs, and this is specifically pertinent to precast concrete. You see trucks going down the road hauling girders or double T's. And with normal weight concrete, frequently they can only get one member on a truck and haul it to the job. But if they reduce the density of the concrete, they might be able to get 2 pieces on a truck at least some of the time. And you can spend a little bit of money on lightweight aggregate, make lightweight concrete, reduce the density just enough, and you can save maybe 8 or 9 or 10 times as much as you spent on lightweight aggregate on transportation costs. So there's huge potential savings. And what does that do? It also reduces the number of trucks on the load. It helps to reduce the carbon footprint of the project. So the effects of the dead load reduction means not only thinner slabs, but generally, because of the significant reduction in dead load, smaller beams, longer spans. The result of that, smaller beams and thinner slabs, means a lower floor-to-floor height. So as you get a taller building, that reduced floor-to-floor height, say in this instance it's talking about 2 inches per building per story. On a 12-story building, that's 2 feet. 24-story, that's 4 feet. So everything that goes vertically in that building is reduced by that amount. So not only do you have savings in the reduced volume of concrete and the smaller beams, but you also have savings in all the materials that go vertically in that building, whether it's the exterior skin of the building, whether it's vertical conduits, pipe, ductwork, anything that goes vertical in a building, you're saving money on. So you have lower construction costs, lower carbon footprint throughout the building, lower global warming potential. Here's an example of a mid-rise building with 30 by 30 bays. You compare this, the lightweight system, to a normal weight system. You have about a 23% reduction in concrete volume in the floor slab, about a 10% reduction in the structural steel supporting the floor, and and a reduced load. So your savings are transmitted all the way down the building into the foundations. And these savings in steel only apply to the floor system itself, the beams and girders for the floor system. There's additional savings available in the columns, and all the way, as I said, down through the foundations. So you add it all up, reduced dead load and reduced volume of concrete means less cement consumption. Everybody likes that because that reduces the carbon footprint. Smaller beams, columns, and foundations, longer spans, fewer columns, smaller columns, thinner slabs, overall material savings the taller the building is, fire resistance, and reduced seismic forces. Lightweight concrete is used a lot out west where in the seismic zones to help reduce seismic forces. So lightweight concrete is a sustainable design option. Now everybody, big focus these days is on EPDs, environmental product declarations. Every industry has produced EPDs. Some of them are company specific, plant specific, some of them are industry average. But almost all EPDs are written on the basis of cradle to gate. That EPD is based on what it takes to produce that construction material and get it out the door on its way to the customer or to the project. That only looks, as I said before, from that webinar 4 years ago, that only looks at one little piece of the pie. What I've shown you just a minute ago tells you that you need to look beyond cradle to gate and look at cradle to grave and even beyond. And the presentations that you'll see today do that. They go beyond the production of the material to how it influences the global warming potential of the entire project. One of the projects that you're going to see later today in the first presentation in part 2 at 11 o'clock is a detailed presentation on this project, Salesforce Tower in Chicago. This was the first project where the Chicago required not only submittal but also analysis of the EPDs of the materials going into this project. And when they did that, they determined that using lightweight concrete instead of normal weight concrete on this project resulted in an overall 19% reduction in carbon emissions. Now you take that information and you go back to that webinar and you say, is that guy right when he said don't use lightweight concrete because it's not sustainable? I submit to you that he was wrong. So in conclusion, structural lightweight concrete reduces the quantity of materials throughout the structure, from the roof to the foundations, saves the owner money because of that material savings, lowers the carbon emissions and global warming potential, and is the sustainable option and makes concrete more sustainable. You'll learn more about that as we go along. That concludes my presentation. Anybody have a question or comment that they want to make before we move on to the next one? Yes, sir. Would I touch on fire ratings?
Explain why it's more fire resistant.
Because the fire resistance rating is based on heat transmission, by and large in concrete, and lower density concrete transmits heat at a lower rate. So the fire rating is based on a fire test. Put a fire on one side of concrete, you measure the temperature on the other side, and The longer it takes for that temperature to rise a certain amount is what determines the fire rating. So normal weight concrete transmits heat faster, so you reach the end point of the test sooner with normal weight concrete than you do with lightweight.